In this video, we will discuss trigonometric functions of real numbers. Now, to begin this lesson, we want to talk about what is called a wrapping function. So, wrapping function will use the capital letter W to represent the wrapping function. We can say W of t equals point x comma y, where W is a wrapping function. And the letter t in that expression is the distance on the tangent line from the point 1, 0. We'll talk about that in a moment. And then the point xy is a point on the unit circle, which is a circle with a radius of 1. So here's a picture of a unit circle, where the circle has a radius of 1 from the center. All right, so the radius is 1. And then we're going to have a tangent line at this point right here. So this point, we'll call that point 1, 0. So 1, 0 is that point. And what we're doing is we're taking another point on this tangent line, such as this point up here, and the length from 1, 0 to this point is called t. That is the length t. And this point, if you can imagine wrapping this line around the circle, so kind of like a string you wrap around a circle, this point is going to be mapped down to here somewhere onto the circle. And that point is the point of point P, which was x comma y. And we can do that for any point. We can take a point down here, which is down in the negative direction. And if you imagine wrapping this line around the circle, that point is going to be mapped down here somewhere to this other point. So this is the idea of a wrapping function. And any point on the circle, any point P, the x and the y value is the same thing as cosine and sine of whatever angle is created. So looking at this point up here, if you create an angle with that, okay, whatever angle that is, the cosine of that angle is going to be your x value, and the sine of that angle is the y value of that point. So if you were told to evaluate a wrapping function, such as this function w of pi over 4, basically what we're doing is we're finding the cosine and the sine. We're figuring out what point does that map to. All right, so we want the cosine of pi over 4, that's your x value, and the sine of pi over 4 as your y value. And you should have that memorized. All right, so cosine of pi over 4 is the square root of 2 over 2. And also the sine is the same thing, the square root of 2 over 2. So your solution to this would be the point square root of 2 over 2, comma, the square root of 2 over 2. So as we stated, anytime you're using this wrapping function, the sine of an angle is your y value, the cosine of the angle is your x value. The tangent is the same thing as sine over cosine, so we would have y over x, and then all your inverses would be just 1 over what we have over here. So cosecant of the angle is 1 over y, and then secant is the inverse of cosine, that is 1 over x, and then cotangent is the inverse of tangent, so instead of y over x, we now have x over y. Now the next thing we want to talk about is the domain and range of trig functions. So we're going to take a look at each trig function and determine domain and range of each. And we're going to begin with the function of y equals sine of x. Now domain is your x value. So what can we plug in for x into this function? Well, you can plug in any number in for x. So the domain would be anything between negative infinity to positive infinity. And now the range, the way to think through this is thinking through the unit circle and remembering that sine is your y component. Well, with the unit circle, the radius is 1. So the maximum y value that we'd see is positive 1, and the minimum y value would be negative 1. So the range of a sine function would be anything between -1 and +1. And that's what we see written here. Y is between -1 and +1. Now cosine is the same idea. So if you have the function of y equals cosine of x, the domain, your x value, could be anything. We can plug in any angle measure in for x. And then the range is the same idea as well. With cosine, that is your x values, and the x values also are limited by the fact that the unit circle has a radius of 1. So the minimum value is -1, and the maximum value is +1. So the range would be anything between -1 and +1. Now let's take a look at tangent. So the function of y equals tangent of x, we want to begin by finding the domain. Now again, for this one, we can basically have any angle to find the tangent of x. All right, you can pick any angle, but there is a limitation. Because remember, tangent is sine over cosine. Okay, and with a fraction, the denominator cannot equal 0. So where is cosine equal to 0? Because it cannot equal 0. Well, cosine is your x component, your x value, and it's equal to 0 when you're up here at 90 degrees, and then down here at 270 degrees. So in either of those locations, you would have cosine equaling 0, thus making the tangent undefined. So notice that it keeps repeating, right? So if you start here at 90 degrees, and you add 180 degrees, that takes you down to 270. Add another 180 degrees, that takes you back around. So past one complete revolution, takes you back up to 90. And then add 180 again, takes you back down here. So this is going to be a repeating occurrence. So another way of thinking of this is 90 degrees is pi over 2. All right, so we take pi over 2. It cannot equal pi over 2, right? So x cannot equal pi over 2, or you cannot add 180 to that either. So basically, a way of writing that mathematically would be seen right here, where x can be any number between negative to positive infinity, except for it cannot be pi over 2 times this right here, 2n plus 1. And the way to kind of think through that, if you forget how to get that, is that if you plug a 1 in for n, right, you would have 2 times 1 plus 1, which would be 3. So that would be 3 pi over 2. If you plug a 0 in, it'd be 1 pi over 2. If you plug a 2 in, 2 times 2 plus 1 would be 5, so 5 pi over 2. So notice by multiplying pi over 2 times 2n plus 1, what's happening is we're getting all these different angle measures. So 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. X cannot equal any of those. All right, so that would be your domain. And then your range in this case could be any number. It could be any positive or negative number, or it could be 0. So it could be anything between negative to positive infinity. And you can verify that because sine and cosine has to be between -1 and 1, right? So if you plug in different random numbers, say you plug in a 1 for sine, and let's say you plug in like a point, I don't know, 0.01 for cosine. Sine over cosine, that would give you a 100 as an answer. Now granted, like this specific combination of sine cosine wouldn't necessarily be a true lineup of numbers, but the idea is the fact that notice when you divide by that decimal, we're getting a large number. All right, or it could be the other way around. Sine could be a small number, it could be like 0, and then the cosine could be some number, and that gives you 0. All right, so just notice the fact it can be anything. It can be a small number, big number, any value. All right, so that's why the range is anything. Now for cosecant, cosecant is the inverse of sine. So the domain is going to be basically the same as sine. except we have a restriction, right? Because cosine or cosecant is 1 over sine. So sine cannot equal 0. All right, so where is sine equal to 0 at? Well, if you think through the unit circle, I'm running out of room to show this, but sine would be 0 here at 0 degrees, and then over here at 180 degrees. So basically, any multiple of 180 is not going to work. So 180 times 1, 180 times 2, it's going to keep, every time you go 180 degrees, it's going to keep going back around to where you started. So the limitation is the fact that x cannot equal any number times pi, times 180 degrees. Otherwise, it could be anything other than that. And then the range is maybe a little tricky to figure out, but cosecant, like we said, is 1 over sine. All right, and sine of x, we said, could equal the range. It could be anything between -1 and 1. So this entire expression could be between -1 and 1. Well, if you get it close to 0, let's say we did 1 over, say, 0.001. Okay, that is equal to 1,000. That's a large number. All right, so it could be a large number like that. It could be a negative large number, if this was a negative. And then if we got closer to 1 for sine of x, so sine of x were closer to 1, 1 is the largest number we could put there, so 1 would be the largest number. So we know it's got to be 1 to infinity. It can be any large number, but it's got to start, can't be any lower than 1. And then the other way is true, so it could be -1, and then all the way to negative infinity. It can be any sort of large negative number. All right, so the way we could write that is that y would be bigger than or equal to 1, or y is less than or equal to -1. Now, if looking at secant, y equals secant of x. This one is the same kind of logic as with cosecant. Secant is the inverse of cosine, right? So the domain is going to be similar in the respect that the cosine domain also applies to secant, but we are limited here as well, because secant is the same thing as 1 over cosine. All right, so cosine of x cannot equal 0, otherwise it is undefined. So where is cosine equal to 0? Well, cosine is equal to 0 up here at 90 degrees, and then down here at 270 degrees. Or in other words, pi over 2, and then 3 pi over 2. So any multiple of pi over 2 starting at 90 degrees does not work. And the way we express that is the same way as we described up here. So x cannot equal the 2n plus 1 times pi over 2. So pi over 2 times this factor of 2n plus 1. And then the range of secant is going to be the same thing as with cosecant, because for the same idea, all right, secant is 1 over cosine, and cosine could be anything between -1 and 1, just like the sine. So the same logic applies here, and the range would be bigger than or equal to 1, or less than or equal to -1. And then the last part on this table is cotangent. Y equals the cotangent of x. So with cotangent, it's going to be the same idea as with tangent. So cotangent of x could be anything. You can plug in anything for x, any angle measure. So this part would be true, okay? But our limitation is a little bit different, because cotangent is the inverse of tangent. Tangent is sine over cosine. Cotangent is cosine over sine. So here, okay, our limitation is the fact that the sine of x cannot equal 0, which was the same limitation as with cosecant, right? With cosecant, sine cannot equal 0, and we have this as the limitation. Same thing here. The limitation is the fact that sine cannot equal 0, and thus we get this. All right, and then the range for cotangent is the same thing for tangent. Okay, it could be any number, any value. So the same logic applies here. The cotangent has the range of anything between negative and positive infinity. Now, switching gears, we want to talk about even and odd trig functions. So we've learned this in the past, but we're going to see it again here in this context. And even, your definition of a function being even is if f of negative x equals f of x. That would be even. And then odd functions, odd would be f of negative x is equal to negative f of x. And what we're going to do is we want to determine which trig functions are even and which trig functions are odd. All right, so that's our objective right here. So if we begin with sine, okay, look at sine of x. All right, what you want to do, the way to think through this, is if you think through your unit circle. Okay, let's pick an angle with a measure of x. Okay, negative x in this case would be down here in the negative direction. That would be negative x. So the question is, how does sine of x relate with sine of negative x? Well, up here in the first quadrant, sine of x is going to be positive. Down here, sine of negative x is going to be negative. They're identical as far as the value goes, the absolute value, but the signs are the only thing that's different. All right, so here, sine of x would equal a negative sine of negative x. Right, because again, if you take sine of negative x, the signs are opposite. So with that being said, this would fall under the category of odd. Right? That would be an odd category. Next, we can try cosine. So cosine of x, how does that relate? Well, if you look at cosine, okay, here again, same angle, we have x and negative x. Cosine for both of these would be the same, right? They're both positive and they have the same absolute value. So here with cosine, cosine of x is equal to the cosine of negative x. Those are the same. So therefore, cosine is an even function. And then we can do the same idea with tangent. So the tangent of x, how does that relate with the tangent of negative x? Well, tangent, remember, is sine over cosine. Up in the first quadrant, both sine and cosine are positive, so tangent is positive. Down in the fourth quadrant, sine is negative and cosine is positive. So the signs are different, which means the tangent is going to be negative. All right, so the tangent of x and negative x are opposites. The signs are opposite. So the tan of x is equal to the negative tangent of negative x. So with that being said, that would fall under the category of odd. So we have sine, cosine, and tangent figured out, and then the inverse functions we can figure out because if the one function is even or odd, the inverse would be the same thing. So if sine of x is odd, then the inverse, cosecant of x, would also be odd. And because cosine is even, the inverse, which is secant of x, that would also be even. And tangent of x is odd, so therefore the cotangent of x would also be odd. Now let's take that information and we'll try to answer this question, determining if this function is even, odd, or neither. So we expanded our question a little bit to include y equals x squared plus cosine of x. So it's a little bit different, but same logic here. So when you're trying to determine if a function like this is even, odd, or neither, what we can do is we can replace x with negative x and see what we get. I'm going to write y as f of x just because it's a little bit nicer. So f of x is equal to x squared plus cosine of x. So what we are doing again is finding f of negative x. So if you look at f of negative x, we would replace x with negative x. So now we have negative x squared plus cosine of negative x. All right, so what we can do, negative x squared is positive x squared. And the cosine of negative x, we want to figure out how does that relate to cosine of x. So again, if you forget, you can think through this angle is x, this angle down here would be negative x, and how does cosine of negative x relate with cosine of x? Well, cosine for both of these would be positive. It's going to be the same thing. They're equal. All right, so cosine of negative x is the same thing as cosine of x. I can replace it with that. So f of negative x is equal to this, which was the same thing as f of x up here. So because f of x is equal to f of negative x, we would say that this function is even. The function y equals x squared plus cosine x is an even function. Now the next thing we want to talk about is what is called a periodic function. Now a periodic function is basically a function that keeps repeating with its value. So here we can express this mathematically as f of t plus p equals f of t, meaning that if we add some value, and that value is called the period, okay, then it's going to be the same thing as this function f of t. So p, the period, is by definition the smallest positive number that we can put there that would make this a true statement. Now how does this work with our trig functions? So let's take a look at sine, cosine, and tangent. So if you were to think of the unit circle and then pick an angle up here in this quadrant. If you were thinking about sine, okay, sine, that sine of this angle would be the same here, and it can also have an equal angle over here as well with the same sine. All right, so these two different angles could have the same sign in the first and second quadrant. So the question is, what number can we add, the smallest number can we add that would make this true every time? What do I mean by that? Well, if you were to pick this angle right here, and if you were to go all the way around the circle one time, so if you add 2 pi, okay, we get back to where we started, and the sine would have the same value again because it's the same angle. All right, and that would be true over here as well with this other angle. If we add 2 pi, so we go all the way back around, okay, it's going to take you right back to here. So 2 pi is going to be the period because that is the smallest number we can add to the angle to make the function, the sine, to be the same. So we can say that sine of t plus 2 pi is equal to sine of t because we can add 2 pi. But we could also add any multiple of 2 pi, right? You can go around a second time, add another 2 pi, and we get back to where we started again. And that's why we have a k right here. It's a constant, meaning we can keep doing this multiple times. So k could be 1, 2, 3, etc., meaning we keep going around and around multiple times. So we would say here the period, this number here, 2 pi, is the period. Now cosine is also the same logic. Okay, we pick an angle, let's say right here. Okay, this angle would have a cosine of some value. And then we pick another angle, let's pick one down here, because this angle down here could also have the same cosine, because cosine is positive for both of these. All right, so assuming the reference angles are the same, cosine would also be the same. So again here, if we keep going around in circles, so you go from this angle around one revolution, so you add 2 pi, we get back to where we started. So 2 pi would be the period. All right, so again, just like with sine, cosine would have a period of 2 pi. So we can add 2 pi to whatever angle we started with, and it's going to be the same thing as the cosine of the original angle. And again, we can multiply by a constant, so not just 2 pi, but 2 pi times any number, any whole number, and that would also be true. Now what about tangent? So if you think about tangent, all right, let's pick an angle up here, for example, with some reference angle, okay, tangent is going to be some positive number, right? Well, where else is tangent positive? Well, tangent will be positive also down here in the third quadrant because sine and cosine both are negative, and when you divide, that gives you a positive number. So in this case, it is true that we could go around one complete revolution and get the same answer. So 2 pi, if you add 2 pi to an angle, it would be true that that is the same thing as a tangent of this angle, but we actually have a smaller number we can use. Notice that tangent is going to keep repeating itself every half rotation. All right, so if you go around just halfway, that takes you to an equivalent tangent. All right, and then if you go around another time, another half revolution over to pi, over to here, that again would take you to the same angle with the same tangent value. So here the period is actually pi for tangent. So we can say that tangent of t is the same thing as tangent of t plus pi, where pi is the period. And notice here we can multiply pi by any number, any constant, right? You can go around 1 pi, 2 pi, 3 pi, 4 pi, etc. It doesn't matter. Tangent would still be the same. Now the inverses of each of these would be the same periods as well. So instead of sine, you can replace it with this inverse. So cosecant would have the same period, and then cosine, the inverse is secant, that would have the same period, and then tangent, the inverse is cotangent, that also would have the same period. Now just a refresher, okay, we have some reciprocal identities that you need to know, and that is that sine and cosecant are inverses. So sine is the same thing as 1 over cosecant, or the other way around also is true. Cosecant is the same thing as 1 over sine. Cosine, we know, is 1 over secant. It's the inverse of secant. And the converse is also true. Secant of theta is equal to 1 over cosine of theta. They're inverses. So to go back and forth between the two trig functions, we would take one and divide by the other. And then tangent is the same thing as the inverse of cotangent. So tangent is 1 over cotangent. And then cotangent is the inverse of tangent. So we can do 1 over tangent to get cotangent. So make sure you have these memorized. And then also, we have a couple more to know, and that is tangent. So tangent of an angle is equal to sine over cosine. So make sure you realize that fact. Tangent is the same thing as sine over cosine. And then cotangent is the inverse of tangent, so which means if you flip the numerator and denominator, we would have cotangent equaling cosine over sine. Now we also have some Pythagorean identities. These ones are new for you, and the first one is related to the fact that if you take Pythagorean theorem on the unit circle, we would do x squared plus y squared equals r squared. But on a unit circle, this r value is 1. And also on a unit circle, x is the same thing as cosine, as we mentioned at the beginning of the lesson. And then y is the same thing as sine. So we would have cosine squared plus sine squared equals 1. And that would be an identity to have memorized. Cosine squared plus sine squared equals 1. Now another one is that 1 plus tangent squared equals secant squared. I can verify this for you by breaking up tangent as sine, so sine squared of t over cosine squared of t. And that's equal to secant squared of t. So with that information, what we can do is we can convert this side over here to have one fraction. So instead of 1, we can write that as cosine squared of t over cosine squared of t plus the sine squared of t over cosine squared of t. And then we can combine into one fraction to get cosine squared of t plus sine squared of t all over cosine squared of t. Well, what did we just say that cosine squared plus sine squared is equal to? That is equal to 1. So what we have, running out of room, but what we have is 1 over cosine squared of t, which 1 over cosine is equal to secant. So we have therefore proven that this expression is true. 1 plus tangent squared of t is equal to secant squared of t. And this way of proving, by the way, is important to know for this lesson. Make sure you're aware of what I did there. So break apart tangent as sine over cosine, and then we can combine that fraction into that expression into one fraction, and then take our initial identity to prove this one. And then we have a third identity, which is seen right here, and that is that cotangent squared plus 1 equals cosecant squared. Now I'm going to verify this one for you as well, but I'd like you to try this one. See if you can do what I did on the second one and do it here on the third one. And your objective is to take this left side and make it equal the right side. Alright, so up here I have the expression, and we're going to try to make the left side to equal the right side. Well, cotangent, we just stated a moment ago, is the same thing as cosine over sine. So what we have is cosine squared of t over sine squared of t plus the 1. Okay, we're trying to get that to equal the right side. Well, 1 we can write as sine squared over sine squared. So let's do that. So now we have a common denominator. And then the numerators we can combine to get into one fraction. We would have cosine squared of t plus sine squared of t. All that is over sine squared of t. And then the first fact that we showed you was that cosine squared plus sine squared is equal to 1. So what we have is 1 over sine squared of t, and 1 over sine is the same thing as cosecant. So we have cosecant squared of t. So we have verified that this expression, cotangent squared of t plus 1, is indeed equal to cosecant squared of t. So here we see all three identities, and make sure you have these memorized the best you can. Especially the first one, because the first one you could use to derive the second and third one, but you cannot without the first one. And if you're trying to remember which ones go together, this is kind of my personal way that I remember, and that is that the cos go together. So cotangent and cosecant go together. So cotangent squared plus 1 is equal to cosecant squared. And then tan would go with the regular secant. So that may be helpful, I don't know, but either way, make sure you have this memorized. Alright, so now we're going to use what we know about sine, cosine, and tangent along with the identities. And here we're trying to simplify a trig expression. So here we have tangent of x times cosine of x times cosecant of x. And our objective is to simplify. Well, what you want to do is take tangent and cosecant. Okay, take those and write them the other way that we have. So like tangent, for example, is sine over cosine. Cosine would just be cosine. Let's rewrite that. So cosine over 1, same thing. And then cosecant, that is the same thing as 1 over sine. So now once you have written it like this, you can tell very quickly what we have, because sines would cancel, cosines would cancel. You're left with 1 over 1, which is equal to 1. So this expression can be simplified as 1. And let's try another type of example where you have to know those different trig functions. And here we are given that x is between 0 and pi over 2, and you're writing tangent of x in terms of cosine of x. Alright, so this information right here tells us which quadrants we're dealing with. And if the angle is between 0 and pi over 2, that would be up here in the first quadrant. So that means tangent would be positive. Now we're trying to write tangent in terms of cosine. Well, we know tangent is equal to sine over cosine, so we can do that, but we want tangent written with just cosine and no other trig functions. So basically, we want to eliminate sine of x and replace it somehow with some derivation or some variation of cosine. Well, what we can do is take that first identity that we were given, the first Pythagorean identity that said sine squared plus cosine squared equals 1. We can take that because it has sine and cosine alone in the same expression. That's why we chose to use that one. Now what we can do is we can rearrange this and solve for sine so that we can replace that, whatever we get, put that in place of sine of x. Alright, so we can solve this for sine of x by bringing cosine squared to the right side. So we subtract that over. Now we have sine squared of x equals 1 minus cosine squared of x. And then remember this notation, by the way. Sine squared means we have sine of x squared. Alright, it's just the way we write it. So to get rid of the squared, we can take the square root of both sides. So we do that. Now we have the squared gone, and we have sine of x on the left, and then the square root of 1 minus cosine squared of x on the right. So now from here, the whole point of doing this part was so that we can replace sine of x right here with this expression that has just cosine. So you plug that in here. Now we have tangent of x equals the square root of 1 minus cosine squared of x. All that is over the cosine of x. And that's what we wanted. We wanted tangent of x written as an expression of cosine of x. And that's what we have here. There's no other trig functions in this expression. So in this lesson, there's a lot of information given to you. And if you try the homework questions, there is a lot of variations of what you see here. So this is just kind of the introduction, and I'd recommend trying practice questions to get more familiar with how you can use this to solve things. And that concludes our lesson for today.